All right, hello class, this is Mr. Lehman. Today I want to talk to you about orbital diagrams. So for my classes, if you're watching this, that means that you're not here at school, you're not doing the live flame test lab, that you are at home and you're doing this while we're doing a lab in class. All right, so let's go ahead and get started. So we're going to take a look in our notes today. Orbital diagrams, I believe, is page 12. So in your yellow packet, in your notes, turn to page 12. And he did a little bit of this in ChemQuest 4B, page 5, and I know we didn't check the answers in class, but orbital diagrams are a visual way to show where the electrons are, which energy levels, which sublevels those electrons are found in, so you have a little bit of better idea, better feel for where they are, and how they're spread out across the different orbitals. So each electron is represented by either an up arrow or a down arrow. If you see an up arrow, that just means that the electron is spinning one direction, let's say clockwise, and if you see a down arrow, that means that an electron is spinning counterclockwise in the opposite direction. That's important when we get into the Pauli exclusion principle, so we'll talk about that here shortly. So arrows represent electrons, and then the orbitals, those electron bunk beds, are represented either by a box, but a box takes a while to draw, so scientists often just use a line. So each orbital, each place where two electrons can go is represented by a box or a line, and we'll look at that, and I'll explain that more as we get to different example problems. Alright, so in our notes, page 12, letter F at the top of the page, it says, orbital diagrams are pictorial descriptions of electrons in an atom. Lines or boxes are used to represent the orbitals, and arrows are used to represent electrons. Orbital diagrams show the specific orbitals in which the electrons reside in, as well as the spin of the electrons, the spin of the electrons, clockwise or counterclockwise. So we need to follow three rules, three principles whenever we're making orbital diagrams. The first one we talked about before, the Aufbau principle. The Aufbau principle is basically electrons occupy or fill the lowest energy sublevel. Electrons occupy or fill the lowest energy sublevel and then work their way up. Alright, so the lowest energy sublevel is the 1s. So electrons are always going to go in the 1s, and then once the 1s is full, the 2s comes next. And so the flow chart, basically the flow chart that we looked at in class this week, that is the Aufbau principle. The electrons are always going to fill up in this sequence, unless they're excited. If the electrons are excited, if we put an atom, a metal atom, in a flame, we can excite the electrons and they can jump around and be in places that they normally shouldn't be. Or if we take a sample of gas and we pass electricity through it, like the spectral tubes like we did in lab number 2, the electrons can gain energy and jump outwards. Alright, so look at this diagram. Here's the energy. Alright, so energy is on our y-axis, and look here, these are the different sublevels. So look, 1s, the energy is really, really low. And then there's a big difference in energy between the 1s and the 2s. The 2s electrons have a lot more energy than the 1s. Once we get past the 2s, the next lowest energy level, sublevel that's available is the 2p. So we put 6 electrons in the 2p, and then look at our energy diagram. Next up is the 3s, and then the 3p. And then look at this, the 4s electrons have less energy than the 3d electrons. So because the 4s electrons have less energy, we're going to put electrons in the 4s, 2 in the 4s first, and then we'll go and fill up the 3d, and then comes the 4p, and then the 5s, and then the 4d. So just because there's a 3 here and a 4 here doesn't mean that we're always going to fill up the third energy level electrons first. We have to go in order based on that flow chart, based on the energy requirements. And that gets a little bit tricky, and if we weren't doing hybrid virtual school right now, we would delve into this topic in a little bit more detail. But we just want to introduce these concepts with you, give you, the rules that work for the majority of the elements, and we're not going to look at the specific exceptions to the rule, unfortunately, due to timing. All right, so moving on. Number 2, the Pauli exclusion principle. The second big rule that we need to follow is that each orbital can only hold a maximum of 2 electrons. So you can never have 3 arrows, 3 electrons in the same orbital. And the only way these 2 negative electrons can share the same space is they have to have opposite spins. All right, we can't have two clockwise spinning electrons in the same space. They'll repel each other too much. And we can't have two counterclockwise spinning electrons in the same space. They'll repel each other too much. So the only way two electrons can share the same space is that one has to be spinning clockwise and one spinning counterclockwise. So that means we're always going to pair an electron with an up arrow, a clockwise spinning electron with a down arrow, an electron spinning counterclockwise. And the third rule we got to follow is the Hunds Rule. Hunds Rule says that electrons will spread out. Electrons will spread out to occupy each individual equal energy orbital before they begin to pair up. So think of the bunk beds back in ChemQuest 4B in the boarding house. All right, we talked about the senior citizens. Before a senior citizen climbs up to the top bunk, they would rather have their own bottom bunk. All right, so there's 3 bunk beds in the pink rooms. Each bottom bunk is filled up before we start to pair up people in the same bunk bed. Well, same thing is true here. Think about this example, this analogy. So imagine that you have, let's say, 2 brothers and 1 sister. You have 2 brothers and 1 sister. So there's 4 kids in your family plus your parents. And you decide you're going to move into a new house. And your family buys a nice 4-bedroom house. And so your parents get a room to share. That means there's 3 bedrooms left. You're going to be forced, there's 4 siblings. You're going to be forced to share a room with somebody else maybe. So you're like, Mom, Dad, I don't want a 4-bedroom house. I'd much rather have a 5-bedroom house. And they're like, all right, we just won the lottery. Let's buy a 5-bedroom house. All right, so you decide to buy a 5-bedroom house instead. Now your parents have 1 room. You and your 3 brothers and sisters can each have your own room. So would you want to pair up? Would you want to bunk up with one of your brothers or sisters and share a room with them when you could have your own bedroom? And the answer is no. You'd much rather have your own space. Electrons are the same way. Electrons want to spread out, have their own space. They only want to pair up if they have to. All right, so let's look at this. Let's try to make sense of this all. Let's make an orbital diagram for sulfur. So first thing you want to do is figure out how many electrons does sulfur have. So look at the periodic table. Sulfur has the atomic number 16. So I know there's 16 protons, there's 16 electrons. There's no charge here, so I know sulfur will have 16 electrons. So first thing we got to do before we start drawing arrows and boxes is figure out the electron configuration for sulfur. All right, so we're going to follow that flow chart. So we got 1s2. The next 2 electrons will go on the 2s. That's 4 electrons. The next 6 electrons will go on the 2p. So look at what we're doing here. We're following the flow chart. So we go 1s, 2 go here, 2 go here, and then we put 2, 4, 6. That's where we're at. The next is the 3s, and then we're going to go to the 3p. All right, that's just the flow chart. We're going by energy. Lowest energy first. All right, so we got 3s2, and then we go to the 3p, and we have only 4 electrons left. So don't write 3p6. We don't have 6 electrons in a 3p. Yes, 6 electrons can go there, but there's only 4 remaining electrons. 2, 4, plus 6 is 10. 10 plus 2 is 12. Plus 4 more is 16. We only have 16 electrons. So that is the full electron configuration for sulfur. For the shorthand noble gas configuration, we would go backwards, and the noble gas group 18 would be neon. For neon, neon always has 10 electrons found in 1s2, 2s2, 2p6. So for the noble gas shorthand configuration, we could write it like this. So now that we got our electron configuration down, we want to say, what comes first? I'm going to draw, not a box, I'm going to draw a line. Lines are easier. So I'm going to have 1s. I'm only going to draw 1 line because there's only 1 orbital. And then after the 1s comes the 2s. I'm going to draw a line to represent the 2s orbital. And then you don't have to use a different color, but I'm going to use red for the 2p. And I'll make this a different color so you can see the color coding here. And then once the 2p is filled, we're next going to go to the 3s, and the 3s only has 1 orbital. And then after that, we'll go 3p4. So for 3p, I need to draw 3 orbitals. I am going to draw arrows. So 2 electrons in the 1s. So 1 electron will have a clockwise spin, and 1 electron will have a counterclockwise spin. And then 2s2. So I'm putting 2 electrons in the same space. 1 has a clockwise, 1 has a counterclockwise. For 2p6, here's the good rule. For the p's, because there's more than 1 orbital, these are the bedrooms, these are the bunk beds. I'm going to put 1 electron in each of the 2p's. That's Hunds Rule. They're spread out, and then if I need to, I come back and I pair them up. So there we go, 2p6. Alright, next up is the 3s. And then next up is the 3p, and there's only 4 here. So I'm going to put 1 electron in each of the 3p orbitals. And it doesn't matter if you put the down arrow first or the up arrow. If I have it, I always put the up arrow first. So just pick one direction of an arrow and just either fill it with 3 ups or 3 downs. But I still have 1 more electron left. Alright, so I need to come back in and add a 4th electron to the 3p, and that'll make one of the orbitals have 2 electrons. But the other 2 orbitals, those electrons are spread out. That's Hunds Rule, right? We got to spread them out. If you did this, that is a no-no, right? We don't pair up electrons when they can spread out to an equal energy orbital that is free. Alright, so spread them out, put 1 in each before you pair them up. So that is the orbital diagram for sulfur. 16 electrons, there should be 16 arrows. Notice if I put 3 arrows in the same space, that's breaking the Pauli exclusion principle. I can only have 2 electrons sharing the same space. 3 electrons in the same space, there would be too much repulsion. They would be trying to get away from each other, and they just wouldn't last, right? It would spread out. Let's do one more together. Here's gallium. All right, so gallium, 31 protons. This is one we did for our example. 31 protons and 31 electrons because it's neutral. So I'm going to write my electron configuration for gallium. 1s2. Oops. There's the first 2 electrons following the flow chart. Next 2 electrons going to 2s. Next 6 electrons going to 2p. Next 2 electrons going to 3s. Next 6 electrons going to 3p. I'm up to 18. Now comes the 4s. 4s2, I'm up to 20 electrons. Then comes the 3d. Alright, 3d can hold 10. I'm up to 30. I got 1 more electron left. So next up is the 4p. There's only 1 electron left. I'm going to write 4p1. I'm not going to write 4p6. I'm going to write 4p1 because there's only 1 electron in the 4p. So that is the full electron configuration. For the orbital diagram, I'm going to draw. I could draw lines, or I could draw boxes. I could draw like box and put 1s, but that's too much work. If somebody has boxes already drawn for you, like on page 8 and 9, that's all right. But for me, let's just draw a line. Alright, so 1 line because 1s only has 1 orbital. And here's one I want to show you, another shortcut. Here are half arrows. Alright, when you get good at this, scientists say, alright, drawing 4 arrows, that takes too much time. I'm going to draw a half arrow. So 1s, the 2s has 2. 2p, I use a different color for the 2p. 2p has 6. So I can go ahead and put 2 in each one. 1 up, 1 down. Then we got the 3s. 3s has 2 electrons. And then we got the 3p. 6 here, 2 in each one. And then we got the 4s. Next up, we got the 3. Let me use a different color for D. Now, D, there's 5 orbitals, 5 bunk beds. Draw 5 lines or 5 boxes. And the 3D is filled with 10. And then finally, we got the 4P. Here's some of these are blue. Sorry about that. I got pink. 4P. And I'm running out of room here. Let me do this. If I had room, I'd draw right. I guess I could draw mini lines. There we go. 4P. You still have to draw all 3 lines, but just pick one of the boxes and draw an up or down arrow in one of the boxes, and that's it. There is the orbital diagram for gallium. So right now, I'd like you to work on page 8, 9, and 10. That is your assignment for today, 8, 9, and 10. Page 8, there's only 3 problems here. Do the full electron configuration, the shorthand, and then look, the boxes are showing the different energies. So you're going to start down here, lowest energy, and work your way up. This takes a huge amount of room. All right, so page 9, we still have boxes, but now everything's side by side. All right, so you're going to do the same thing, show electron configuration, draw the arrows for page 9 in the boxes. And then page 10, you're simply going to write down how many electrons are present. So like here we got nitrogen. Nitrogen has 7 electrons. So 7 electrons, draw the full electron configuration, and then show where those 7 electrons are. For phosphorus, P has 15 electrons. I would draw the 15 electrons. And once again, go left to right and follow those rules. Follow the Aufbau principle, go in order, lowest energy, up. Follow Pauli exclusion principle. You need to have 2 arrows and 2 arrows only, opposite spins in the same orbital. And then follow Hunds Rule, right? Spread out the electrons in the orbitals before you pair them up. All right. If you need any help, send me a message. Have a great day, everybody. Take care. And I'm going to stop this recording right now.